So here we're going to consider the two vectors u and v, and we're going to work through a series of questions about them. So part A is to find the unit vector in the direction of u. So we'll start with that. So we can figure out a unit vector, which is going to be u with a hat on, as being equal to whatever the original vector u is, divided by the magnitude of it. So we've already got what the vector u is, we just need to figure out the magnitude, and we can get that by doing the square root of our components, which is 6 and 4. We square them and then add together, take the square root. So this is going to become the square root of 36 plus 14, which I believe goes to 52. Alright, so now we're going to substitute up in here. So u, I'm going to sub it in the form where we define the i's and the j's, just because I prefer that. So 6i plus 4j divided by the square root 52 that we found. So I'm going to restate this a little bit neater, where we have 6 divided by the 52 as our component in the x direction, and then we're going to have 4 divided by the square root of 52 as the component in the j direction. So that there is a unit vector in the direction of u, and just remembering that a unit vector means that it has a length of 1. Okay, so I'll scroll back up. I'm going to move on to B now, which is to find a unit vector which is perpendicular to both u and v. So I might do that over here. So the first thing is that we need to find a vector, not necessarily a unit one, which is perpendicular to both of these ones. Now, the way that we can do that is to apply the cross product, because we know that the cross product is always going to produce a result of a vector perpendicular to whatever you consider inside the cross product. So I'm going to define a new vector v as being the cross product of, a new vector w, which is going to be the cross product of u and v. And this should result in a vector which is perpendicular. So if we substitute in our expressions, again, I'm going to use the I and j version of writing this out rather than the brackets, just because I prefer it. So 3i plus 1j. And now we need to expand out these brackets, remembering that each term needs to be multiplied or cross product against everything else in the other bracket. So here I'm going to start with 6i crossed with 3i. Now we have I cross I, which we know goes to 0, so that one's quite easy. So next up we have 6i crossed with 1j. So we are going to get something out of this since we have different unit vectors being crossed. So here if we do 6 times 1, it ends up being 6. And I cross j, more correctly, we can get from our little diagram. So I cross j is in the direction of the arrow, which means it's going to be positive, and we get the other one out, so it's going to be positive k. So 6 times positive k is going to be positive 6k. Next up, we have 4j crossed with 3i. So 4 times 3 is 12, and j cross I is the opposite direction to the arrow here, so it's going to be a negative, and again we get the other one out, so we need to multiply by negative k. Pop that in. And the last one, we have 4j crossed with 1j. We know a unit vector crossed by itself goes to 0, so that one's quite easy. So overall we get 6k minus 12k, which is negative 6k. Alright, so this is a vector which is perpendicular to u and v. Just be aware you could have equivalently done v cross u, so the opposite here, which would have resulted in this one being the opposite direction. So you would have got out the vector 6k instead. Okay, so that's if you do the opposite. This would be equally correct, okay, because it's just asking for a unit vector, not the unit vector. Okay. So we'll move on to converting this into a unit vector. So we just need to apply this methodology again. So the unit vector in the direction of w will be w divided by its magnitude. So if we want the magnitude of w, this is going to be really easy, just because it's only got one component. So if we square that component and then square root it, it's just going to come out to 6 on its own. So if we go back and pop it into this equation, we're going to get negative 6k divided by 6, which is just negative 1k over all. So this represents a unit vector perpendicular to both perpendicular to both u and v. Again, just be aware, if you were doing this alternate way, which is equally correct, you would have ended up with this being positive 1k for the unit vector in the direction of 6k. So for part C here, we're asked to find the scalar component of u in the direction of v. So this is thinking about kind of projecting one vector onto the other and looking at kind of how much goes in that particular direction. So I'm going to do a little bit of a sketch, all right, of what this looks like. So let's draw our two vectors u and v. So if we start with u, it's 6i plus 4j, so maybe something like this. And then we've got v, which is equal to 3i plus 1j. So I think it's going to kind of be underneath it a bit. Maybe something like this. So for C, what we were asked is to find the scalar component of u in the direction of v. So that's the important part there. We want to project essentially u onto v and see how far it extends in that direction. So if we look down here, the direction of v is like this here. So we want to project this vector down onto it. So I'll pick a different color. So it's going to be this bit, and we're going to have a right angle that forms in here. So this green thing now is our projection. Oh, I think I've got that backwards. Okay, so the projection of u in the direction of v. Now we're not actually trying to get out the vector version of this. What we're trying to get out is just the scalar component, or the length of this line. So how we can do that is there's an equation to find the component in that direction, and it's essentially the dot product of the two vectors you're considering, and then you divide by the magnitude of the one that you're considering in the direction of. So that's going to be v in our case. So if we go through and figure out our dot product, so u dot v, it's going to be 6 times 3 plus, then we've got 4 times 1. So this is going to be 18 plus 4, or 22. And then if we look for the magnitude of our v vector, it's going to be the square root of, it's our 3 squared and 1 squared. So 9 plus 1, which is square root 10. So I can go back and substitute up in here. So we're going to get 22 divided by the square root of 10. So this here represents the length of that green line, or the scalar component in that direction. Yeah. All right. So we have one part left, which is D. And this is now to find the vector projection of v onto u. So this is kind of like the opposite case. So for this first one, we were projecting u onto v. Now it's v onto u. So I'll come back down here. And for part D, I'm going to redraw our sketch. So the u and v vectors are exactly the same as before. But this time we're projecting the other way. So this here is the direction of u, and we want to drop a right angle here and pop v onto u. So it's going to be like this part in here that we're solving for. So now this is the projection of v onto u. So to figure this out, there's an equation that we can substitute into. So our projection is equal to the dot product divided by the magnitude of the one we're projecting onto, so in our case u, and this gets multiplied by essentially the unit vector in the direction of u again, the one we're projecting onto. So let's go through and figure out what we don't know. So I think the only thing we haven't so far worked out is the magnitude of u, because the dot product we had a moment ago. So let's go through and get this. Our components are 6 and 4. So square root of 6 squared and 4 squared. Actually, I think we did do this before. It came out to the square root of 52. So if we go ahead and now substitute into our projection, we worked out this to be 22 a moment ago for the dot product, divided by the square root of 52. U, again, I'm going to write it in i's and j's just because I prefer that, but our components were 6 and 4. So 6i plus 4j, and this gets divided by our magnitude again, which is 52. So if we multiply this out, of course we need to do our bracket expansion here. So the top line here ends up going to 132i and 88j. And then square root 52 times square root 52, the square roots cancel each other out, and we're just left with the 52. So we can write this as the two parts on their own, so 132 on 52i and 88 on 52j, and those fractions do cancel down a little bit, so equivalently this is 32 on 13 and 22 on 13. So if we go and have a look at what this kind of looks like on our diagram up here. So what we're trying to look at is this green line, our projection. So if I pick a different color, what we're saying is that the vertical component is the 22 on 13 that we figured out, and the horizontal component here is the 33 on 13 that we figured out. And that kind of looks right because it's bigger in that x direction than it is in the y direction, and both of our components came out positive, which is in these directions that we've drawn. So it all does appear to be consistent. So that's all I've got for this video.